In this section, we're going to talk about the rates of change in tangents to curves. A good application of rates of change is average and instantaneous speed. Before we talk about speed, let's remember Galileo's law. In the late 16th century, Galileo discovered that a solid object dropped from rest, not moving, near the surface of the earth and allowed to fall freely will fall a distance proportional to the square of the time it's been falling. If y denotes the distance fallen in feet after t seconds, then y equals 16t squared. We'll use this formula for our next problem. A rock breaks loose from the top of a cliff. We want to look at its average speed during the first 2 seconds of fall and during the 1 second interval between 1 second and 2 seconds. Okay. To find the average speed, we're going to divide the distance covered by the time elapsed. We use the notation delta y to denote the change in our y values, or the change in our distance, divided by delta x to denote the change in our x values, or the change in our time. If we use the formula y equals 16t squared, then at 2 seconds, our object will be at 16 times 2 squared distance. If we subtract from that the distance at 0 seconds, that would be 16 times 0 squared. That will tell us the change in our distance over those 2 seconds. We're going to divide that by the change in the time. We've gone from 0 seconds to 2 seconds. If you simplify the top, you'll have 16 times 4 minus 16 times 0, which will give you 64 on top, and 2 minus 0, which is 2 on bottom. Our average speed during those 2 seconds would be 32 feet per second. Now during the 1 second interval between 1 second and 2 seconds, we'll again look at the change in our distance divided by the change in our time. The change in our distance is, at 2 seconds, our distance is 16 times 2 squared, and our change at our distance at 1 second is 16 times 1 squared. Our change in time is that we go from 2 seconds to 1 second. So on top we have 16 times 4, which is 64, minus 16 times 1, which is 16, and we will divide that by 1. That's 48 divided by 1, or 48. So between the 1 second and 2 second time marks, the average speed was 48 feet per second. Now we really want to look at instantaneous speed. Instantaneous speed tells us the exact speed at any given point in time. If we start looking at smaller and smaller intervals, for example, we looked at 1 second, and between 2 seconds and 1 second, our average speed was 48. You'll see in the table, the first row, we're looking at a length of time interval 1, and our average speed was 48. As we start making those time intervals smaller and smaller, so if we go from 1 second to 1.1 seconds, and from 1 second to 1.01 seconds, and from 1 second to 0.001 seconds, we start having smaller and smaller intervals. If we could keep this up and get our h to be closer and closer to 0, we would get closer and closer to the instantaneous speed at 1. This concept is the concept of limits that we'll be developing over the next few sections. You'll also see in the last column, we look at time seconds at time 2, and we look at a 1 second interval from 2, and then an interval of 0.1 seconds from 2, and so forth. And you can see that in each one of these cases, at time 1 and at time 2, the average speed is getting closer and closer to a set number. At 1, it appears to be approaching 32, and at time 2, it appears to be approaching 64. Now this concept of average rate of change can be used for things other than speed. If you look at the formula at the top, your change in y divided by your change in x can be given in two different forms. The first form should look familiar to you as the slope formula. When you developed the slope formula in algebra, you usually used y2 minus y1 divided by x2 minus x1. Here we have f of x2 minus f of x1, which is the same as y2 minus y1. The other form, f of x1 plus h minus f of x1 divided by h, is the same formula, just in a different form. If you look at the picture, that will show you the relationship between the two. The picture there is of a secant line between 2 points, a point x1, f of x1, and a point x2, f of x2. To find the slope of the line, secant line, we can do the f of x2 minus f of x1 divided by x2 minus x1. Or we can think about the change in the x's as being h, and we can develop the last formula. In certain cases, one formula is easier to use than the other, and so as we work through problems in this book, we will be sometimes using the first formula and sometimes using the second. Now here is a picture that explains to you the relationship between tangent and secant lines. If you look at the secant line between P and Q, and you think about Q becoming closer and closer and closer to P, so as Q approaches P, the secant line will get closer and closer and closer to the tangent line. Again, this is the concept of limits that we'll be talking about in the following sections. Now one thing we're going to do is we're going to look at functions and we're going to find the slopes of tangent lines at certain points. Here we have the parabola y equals x squared, and we want to find the slope of the tangent line at the point 2, 4. If we know the slope of that tangent line, then we can actually write the equation for the tangent to the parabola at that point. Now we are going to use the first form of the rate of change, which was the change in y divided by the change in x is equal to f of x1 plus h minus f of x1 divided by h. Now, in this case, our x1 is going to be 2, because we're going to look at the x from the point. Okay? So we're actually going to be doing f of 2 plus h minus f of 2 divided by h. Well, if we do f of 2 plus h, then we're going to take 2 plus h and plug it into the formula x squared. So that will be 2 plus h squared minus f of 2 will just be 2 squared, and we're going to divide that by h. Okay. Now, if I simplify the top, remember to square 2 plus h, you either use the formula for a trinomial square, or you write 2 plus h times 2 plus h and FOIL it. That will be 4 plus 4h plus h squared. And then 2 squared is going to be 4. Now, when I simplify on the top, you'll notice that the 4's cancel. I have 4 minus 4, so that leaves me with 4h plus h squared divided by h. If I factor an h from the top, that will be h times 4 and h times h. Then I will have an h on top and bottom that I can cancel. And my formula for the rate of change, or the slope of the tangent at that point, is 4 plus h. Now what we want is we want for h to become smaller and smaller and smaller and eventually become 0. If h were 0, then our slope would be 4. And so the slope of the tangent line of the parabola at that point is going to be 4. If we want to write an equation for the tangent to the parabola, then we'll just simply use our slope-intercept form, y minus y1 equals m times x minus x1. And so we'll say y minus, and our y value here is 4, equals our slope times x minus our x value here, which is 2. We can simplify that. This would be y minus 4 equals 4x minus 8. And by adding 4 to both sides, we'll come up with the equation, which is 4x, y equals 4x minus 4. So the equation of the tangent to the parabola at the point 2, 4 is y equals 4x minus 4. If we look at this picture, you'll see we develop the secant slope as they did at the top, which is h plus 4. As h becomes closer and closer and closer to 0, then our tangent slope will become 4. You can see the picture here. The pink line is the tangent line to the parabola at the point 2, 4.